Thanks everyone for coming. Maybe I should have precised in the title that is actually local LLMs that we're going to see. So we're going to use easy tools and build up the pipelines ourselves. There's some maybe much more bigger tools that are starting to be developed to do these, but it's always good to have a sense of how to do it with easy tools, small tools, yourself. So, pipelines for biomedical semantic search. So semantic search, vector search, it's all kind of the same thing. So just a bit of background, computer science engineer, bioinformatics PhD, self-trained in NLP. I did a bit of Twitter withheld content analysis. 3 years wannabe founder, web app for real estate market, and a bit of storytelling also. So I joined Harvard Medical and Professor Tsai, January 2024, research associate. So what they do at that lab is translational data science. Name is learning a health system. And what we actually do most is analysis of electronic health records. So hospital visits, codified data when you go to the hospital, diagnosis performed, the medications prescribed. That's all the data we're looking at. A big part also is the clinician's notes that will detail a bit why some diagnoses have been performed, why some medications and not others. Can be insurance reasons, can be side effects, estimation. So one of our big collaborators is Mass General Brigham, one of the leading hospital in Massachusetts, and we also work a lot with Veterans Affairs. We have 3 main disease we study: rheumatology, multiple sclerosis, Alzheimer, but we also do methods for general biomedical that can be applied to any kind. And one of the big research area of my professor is transfer learning from large to small hospitals. So when we have a lot of data from the large hospitals, and so to enhance the information we can extract from the small hospitals, but while still maintaining patient privacy, data confidentiality. So I was employed to work half-time on suicide prevention project and half-time on lab level and multiple projects. So for suicide risk prediction, we're trying to help clinicians follow up in priority with the at-risk patients. And so we use codified data I talked a bit about, and NLP on clinicians' notes, which helps a lot, especially in the mental health areas, but also in general diseases. So some of the 3 things I've been doing, apart from that on the lab level, is a dictionary codebook where we map hospital variables, local variables to standardized classifications. So this will be the ICD, International Classifications of Diseases. And I also do a lot of our Shiny apps with JavaScript, INS some of their apps. And so since I'm a bit of industry pharma background, I know a bit of quality processes that helped quite a lot. Reproducibility for me is quite a big thing. Open science, like open data sets, all the way to Docker image. This is a little example of a talk I gave last year. Here's a QR code to my website where you can find the talks, some of my writings. We'll come back to the QR code. So here what we see is the correlation matrices between the concepts. So we have the diagnoses, and so with these kinds of graph, we can investigate. It's kind of research-based app for us to make sure that our models are working correctly. This is not the kind of things we'll show to the clinicians directly, but it's more for us to troubleshoot our methods. This is an example of the dictionary codebook I was talking about. So this is fiwascatalog.org. It's a resource that we use. Here we have the ICD classifications. So we have a lot of different classes, a lot of details, and we have what we call a fee code, which will be the more broader group that we will actually analyze to have statistically meaningful groups. So this will be a big part of my first part. I've been doing this semantic search on these kind of dictionary codebook. So it all started when my professor asked me, oh, could you do us an Elasticsearch embedding-based app? So I didn't really know what that was at the time. And since on my resume it was written that I did things with Elasticsearch, she knew that it would be a great match. So I found this cool blog post, Dylan Castillo, which I highly recommend. Maybe the only troubling part is that it uses a virtual environment and not Docker, and that cost me quite a lot of time. But so here you have a bit complex diagram, but what's going on is, so you have the browser, user, that's the web app that the user accesses. You have the vector database, the indexer, the documents. So documents is what we're going to search into. We index them, we put them into the vector database, and the search app retrieves them from the vector database. So you give a query, it looks at the closest documents, and it returns to you the documents. And that was kind of a nice moment for me. I haven't really worked with Elasticsearch. I heard that it would be useful to search on elements with many number of characteristics, but I didn't really get what that was meaning. And so I've been using vector embeddings to represent words quite a lot, and that's when I kind of make the match. Oh, so we could actually store the embeddings in Elasticsearch and query them directly. So I guess a lot of people are not really confident with embeddings. I'm going to give a little primer, very crude, but this should get you up and running. So in 2013, there was Word2Vec coming out, which made quite a lot of noise. And so the latest natural language processing are kind of similar. So imagine you have a paragraph, several sentences. Say each time 2 words appear in the same sentence, you give +1 similarity to that pair of words. You build up a matrix with each of your unique words, and you have your similarity values. And this matrix enables you to ask what are the 5 words most similar to word X. So this is symmetric matrix, similarity matrix, and probably you heard in a lot of the previous talks, they was talking about OpenAI embeddings, for example, that they were querying. So here is an example where you're building yourself these embeddings. It can be useful for data privacy when it's patient data. It can be useful when you want to train specifically on one kind of data. But most of the time, these big natural language processing methods like ChatGPT, when they train on a huge amount of data, that's when they get much better. So you can do it your way, but it's usually better to use pre-trained models. So like I was saying, ChatGPT, they're not really doing similarity matrices, they're rather doing neural networks, but they still provide these embeddings. So when you query OpenAI embeddings, it's something that they kind of reconstructed just for you to be able to use it. You can see it a bit as the last layer of the neural network, but it's not even really that. So why is it so useful? Because it can guarantee you no hallucinations. So my first scientific encounter was hallucinations. I was doing these embedding retrieval. I had these, so I'm querying obesity, it gives me 10 variables. Let's say overweight, anorexia, bariatric surgery. So like the next step would be, oh, well, can you regroup them? Do you see the commonalities between them? Because what we see is that they're synonyms, there's like a parent family of class, eating disorders, and more like medical consequences. And after maybe 10 passes, prompt engineering, asking my LLM friend, he's telling me, yeah, you should ask him to do a tree. Well, after a while, he starts including a variable that was not in the 10 that I was giving him. So this is inherent knowledge. But so it is quite problematic because even with a RAG system prompt, where you actually tell the LLM, use only the list provided, you're not even doing jailbreaking or whatever. It's just that since you're giving few sets of commands, at one point he just doesn't think that the first one was that important. And so my guess is that the more you add prompt complexity, the higher the risk of hallucinations. So when you're doing this kind of stuff, you want to keep your prompt quite easy, not too complex. These last days I saw some very big prompts, so I think it works, but depends on the use, and you need to be careful about that when you're doing new prompts yourself. So I'm going to insist a bit on this. Let's imagine a more like concrete example. You have a biomedical data set, you have maybe a few variables, 1,000 patients over some time, body mass index. You ask ChatGPT, here's a list of variables, which ones should I study to best predict cardiovascular? It will tell you out of the 300, these three, and then you'll notice, but 2 out of 3 are not in the list. So this shows why we prefer to use embeddings in our methods. We have less natural language understanding. Negations are not managed at all. If you say not bipolar, it will just understand bipolar. But you have more control and output. You can make sure that everything you retrieve is in your database. So this is what the first app looked like. So the rows here are all the variables that I map to standard ontology and then to the group codes. So here you have the hospital code, standard one, and the group one. And so we have 1.4 million rows. So we give this to the pre-trained model. We build the similarity matrix. So it's actually a similarity matrix that we perform dimensionality reduction on it. So that's why we call it embedding matrix. And then we can query new words. So the cool example here is you type in bipolar and you get lithium, which is a known medication for bipolar. And what I think is a cool example here is that it shows it's not just finding synonyms, it's actually finding treatments. And so this is BGE based. BGE is a model from a Chinese team. In literature, it shows it's quite often very good, better than most. And my talk will be especially about how I compared BGE to other models, how I built a pipeline to be able to easily compare all these models, and so for my dictionary app to have the best embedding model that I can find. And so these are pre-trained models. Compared to OpenAI embeddings, you won't need to buy anything. You don't need to pay each token. You just need to download the model once. So little schema, 1.4 million descriptions. We first do the indexing. That's where we're going to use Pytorch, LangChain. We put it into Elasticsearch. Each of these descriptions has representation of 1,000 numerics. This is all stored in Elasticsearch. It weighs around 15 giga. And then for each user, query a word, do the representation on the fly, do the cosine similarity with your database, find closest words based on their representations. So Pytorch enables you to index with your GPU, but LangChain is quite important here to enable vectorization. So computing a word, so usually I will have maybe sentence length descriptions. In previous talks, we talked about how should we chunk documents to do the embeddings. So here we don't have this problem. We're just doing small. And so each representation is computed fast, but our problem is that we have a lot of representations to compute. So if you just do an array for loop, your GPU will be really underused. And that's where vectorization and LangChain is really useful. And so these descriptions, I index them in 25 minutes on a low-grade GPU for $300. But get things right with a for loop for start. And so once you index this, you can use the Elasticsearch functions. There's native functions to perform cosine similarity. You're not going to need to bring up your whole matrix in memory. You can do this basically on 8 GB RAM, even if your similarity matrix is much bigger. I want to show a bit that the code is quite small. There's a lot of redesigning that goes on. Keep it easy. The cool thing is LangChain. So here we have the function Elasticsearch store from documents. So you basically give it your list of documents, your embeddings function. So this will come from Hugging Face. You download it with this. And this is basically everything you do. This stores it up in your Elasticsearch. You need to have your Elasticsearch instance running up here. And this will populate your similarity matrix in your DB. Here we see the Docker compose. So the upper part is where I define the Elasticsearch, and the lower part where I define the indexing. Here you can see I'm deploying with a GPU. The build refers to this Docker file, also quite small. So I just install a few Python libraries, Elasticsearch, transformers. And so Docker Compose is really useful here to be able to connect to the Elasticsearch instance easily. And once all this is done, I come back to my RShiny app. I prefer to develop in that. We can write quite complex web apps in very short source. And so this is like how my web app is actually coded. And we have our package that does the interface to the Elastic database. And I actually first do the indexing on my local computer. Then I populate my server with the pre-indexed database. And I open the RShiny app on AWS. And this is where the fun begins. Because one model is all fun, but what about the other models? Some other models are trained only on biomedical data. Shouldn't that be better? Well, looking manually, we can see that BGE is still better, but there's even more like BERT. And this time literature actually says it should really be better, but we don't really have convincing benchmarks like easy to reproduce code. So that's why I kind of took this path of, okay, which pipeline am I going to build to be able to do this, to be able to compare maybe 5, 6, 7 models. And so I already been using a bit in our laboratory. We have known pairs. So it can be clinician curated, so expert knowledge. We'll have things like first concept, schizophrenia, related to second concept, psychosis, and how we measure our prediction model's performance is that we query schizophrenia. If the top matches, maybe 10 first matches, have it, then we say, okay, it's good. So this is like the easy way to explain it. The more rigorous way is AUC, we random null pairs. This also helps us to find good similarities thresholds. And we can say, okay, at this threshold, we have 5% false positives. And for a clinician that's looking at this app, he wants to have automated ways to know how much variables to return. Because maybe one variable will have 100 variables related, maybe another one will have only 10. That's why we don't want to have a fixed number of variables we return. We want to base it on actual clinician usefulness. So this can be derived by clinicians. It can also be mined in scientific literature. There's different ways of constructing them, and it's quite important. I'll come back to it. And so this is our data set of true positives. But how is the actual design going to go? Previously, I had this two-step indexing deployment. I'd like to keep it quite close to my app to not have to have completely different environments. I already have an R package to do these models' performances. So this is where I start wondering in which way I'm going to connect all these components. I already have a Docker Compose calling a Makefile. Maybe I could do a Makefile calling a Docker Compose. Maybe I could put R in the Docker image, Pytorch in the R image. What I actually went with, let's just do a first Makefile, root level, Docker Compose, and then other Makefiles. So here on the right, have the folder structure. First Docker Compose, ESLang will be the Python folder. Relastic will be the R folder. So like this, we keep everything separate. We have our Pytorch running fine. We have our Shiny running fine. We don't mix them too much. And in our Makefile, we call our different Docker Compose rules. We first build our evaluation dataset, move it to Python, index, store it in ES with the Docker volume, and then from R, we can access the Docker volume easily. This is what the Docker Compose looks like. First rule will be this write evaluation. This will be the Elasticsearch. It's very similar to the one I showed previously. The indexing. And the new, where I call the Kgraph package to measure AUC. Just call make, cat the text files in which it writes. Doesn't take more than a few minutes. We have something like 20,000 pairs. And we have these 6 models I'm comparing. So these are all pre-trained models. And this enables us to say, okay, highest AUC is the one we want to use in our dictionary. And we can take it a step further by investigating a bit our pairs. So in our pairs, we can have diagnosis relationships, such as what I was saying, schizophrenia, psychosis. And we can have medication diagnosis, like bipolar lithium. And what we can see is actually all these models, they perform much better when you're doing just diagnosis to diagnosis. And when you try to predict a medications that used to treat a disease, it's much harder. And so it's kind of related to synonyms to pairs that are similar or related. And what we usually do in our lab is that we have knowledge graphs that enables us to get better performances on these non-synonymous. And a lot of the time, the diagnosis to diagnosis relations will be almost synonyms. Wanted to touch base a bit about fine-tune BGE. One of the limitations I saw when I was typing for schizophrenia, so maybe we had 200 variables returned. And most are good, but we also get some strange outliers: bacteria, leukemia, pneumonia. There's a common thread here. It's the suffixes, and so it's because of tokenizations. It's because of how these neural networks work. Because they're kind of breaking down words in smaller chunks, taking roots. And so for very common word, let's say happening, they understand that ing is, there's happen and there's ing. But for more rare words, so like the more frequent the words, the more it finds the commonalities. And the less frequent, the less it will treat the word as just one big word and not decompose it. That's how they kind of do character level without really doing full character level. They chunk up words as it's more and more important. And so in practice, what we get is that the more rare words, they're considered similar just because they end by the same letters. And so I heard a bit about fine-tuning these last days. Some people were saying that it's quite expensive. There was even in specific teams some debates on should we do it or not. There's also some consideration on, are you taking the model out of its first course? Are you biasing it too much? Are you overfitting? And so we tried also a bit, tried inputting a lot of biomedical pairs, fine-tuning, but I mean, I think one of the fundamental limitations is that the original teams, they had quite a lot of resource. They trained it for 1 month or more, and you're trying to do in a few weeks GPUs. So it's quite hard to do something better than the original team. But if you focus just on the errors you notice, then that's where you can do actual fine-tuning that will give you a better performance. So I did this with our intern. In my latest dictionary app, we're now using the fine-tune BGE. It was like all the different methods we tried with a lot of medical pairs were not really working. And the only thing that worked was when we were just focusing on words with common suffixes. So this is the app that came out of my intern Joseph Hoch's work. So what we're doing here is clinical trial search. Type in a condition, it will give us the clinical trials. So this is just an API call. But the more interesting part is that we're embedding the title and the summary. And then we're going to query PubMed articles. So we're fetching publications that are similar to the clinical trial that we want to study. So this one was menstrual cycle and weight loss. And in the publications, you will have menstrual cycle and weight loss related publications. this was first part, half an hour. And so this was like my pitch for scale. One of my first line of my abstract is that, oh, well, hallucinations is really a limitation. Let's just use embeddings. But my most recent developments, I'm actually using Llama. So I had a new use case where Llama proved really useful. So it's a bit similar, but a bit different. So unified medical language system. Here this time we have a dictionary of 5 million codes and descriptions. And we'll have a lot of, for one code, the different ways of saying it, like the synonyms. And it can also have the plurals, the acronyms. And in these codes we have relationships. We can have more or less complex synonyms, parent-child. So usually what I was saying about the standardized code and the group level code. So usually the more detailed codes will be the child of the group code. And so we're using this quite a lot on our clinicians notes. And one task we're spending a lot of time on is to do roll-up of these codes, because some are very specific, and to analyze them usefully, we need to regroup them in larger groups. So I'm using Llama, which is Facebook's open source version of ChatGPT. Open source in the sense that it's a pre-trained model that you can download. So UMLS, 5 million codes, parent-child relationships. So I told you my research project is suicide prevention, so in this part we're going to focus a bit more on this. Here's an example of parent-child relation. One of our complexity is that we don't really know at which level to stop. We could use the frequencies to say, okay, now we have something that we can use statistically, but it could also be cool to have a study-independent dictionary that we can just use without needing to go into our data. And so this parent-child relationships, the graph, enables us to do a first, to understand the structure of the variables, but it's hard to really regroup them in meaningful groups. You can use graph properties like subcomponents, so basically the number of child one node has. Degree will be the number of inputting edges. And so first experiments was decent, but you get very small groups. It's not really ready for use yet. So I started taking another pass, guiding this roll-up with the codified dictionary we saw before. So we already had like schizophrenia with acute disorder would roll up to schizophrenia. So we're going to say, okay, these are the group levels we want. This will guide us. So what I'm doing now is start by finding the exact string matches. Then we use the synonyms and the parent-child relationships. But even then, we only have 10% of the 5 million mapped. And so within those 10%, one of the most important things are the fee codes, the group level diagnoses. And for them, we have more like 60% mapped. So quite good, but we still have a bit to do. And in particular for my field of research, so one example of why it didn't match with the exact string match will be because in the fee code it was saying suicide or self-inflicted injury, and the CUI will be N. So it's not very far, but we do have to be careful with partial string matching. We don't want to map type 1 diabetes to type 2. Another core problematic this is an example of the suicide fee codes. We basically have one group, either ideation or attempt, and then two subcomponents, the ideation and the attempt. And we want our QE mapping to follow this hierarchy. And with the graph properties, I could get good mappings, but I would basically have the same QE for the two fee codes. So that's why I finally gave up on the graph properties, starting taking the Llama road. So we have the risk of hallucination. We're not going to do it on too much. We're going to quality control it so roughly, but I actually discovered it's not the worst part. So what we can do is we do a first filter with the BGE embeddings I was talking about. So we get 30 most related variables, and we input this to LLM. Which one is the best match for the string we're trying to map? And so giving this to Llama in the terminal and ChatGPT in the browser, Llama gave me suicidal behavior, which was actually the one I was trying to get. ChatGPT suicidal ideation. Was quite impressed that Llama was doing a better work. So this is 3.1, 7 billion parameters. But the thing is, LLMs are not really reproducible. Once integrated in Docker Compose with the API call, oh, so sorry. Here's the hotline to talk about your thoughts. Or other variants of that, or the word I was not looking for. And so one of the things we're talking about is that temperature parameter will lead your results to be more consistent, but I can tell you that from my experiments, it doesn't work. So I was kind of stuck on that. But I was still quite impressed by the fact that I found the suicidal behavior one. So since I saw it working once, I knew I could do it again. So one of the cases that was annoying was that he was giving me suicidal ideation. Here, one of the big step that enabled me to move forward, you include the variables that you actually don't want. Here's a list. You cannot use these variables, and you enter the text descriptions of the variables you don't want. So in my prompt, I also say, like, answer just this, nothing else. And the safety answers, managed with a few loops, kind of manually done. And I had one other safety error related to violence towards women. So it's actually just like a diagnosis of gynecology related, but the LLM tells you, I can't help you with that. So to be able to just, like, since I'm going to need to quality control all these mappings that the LLM is doing, I want to do most as I can myself, classic methods like string distance. So I'm applying this on the lower level, and then as I go up in the hierarchy, that's when I use BGE and Llama. So I use it to do maybe 300 fee codes with 10 loops. So the two safety errors are the ones that require me to do the loop, basically. At the end, I'm still stuck on one that has an hallucination. So it's telling me, yeah, it's this variable, but it's not the variable I gave him. But it's not really a diagnosis that is so relevant either to me or very frequent. So I'm leaving that to someone else. So it works for me. And for me, the word of the end is that it's actually more about the safety than the hallucinations. The LLM will stop you, and you have to find ways to still ask your clinical questions. Few notes take away. So semantic search, embedding-based, vector search, it's all the same thing. The first part of a RAG, you have hallucination-free guarantees. To use LLMs, you'll need to constrain and control what it's doing, do as much as possible with classic methods. Even after the LLM did its part, there's kind of a post-processing step. And these known pairs and benchmarks, very valuable. I think they will become more and more. It takes a lot of domain experts' time. You can imagine that clinicians have other things to do. And often I think that when we see benchmarks on Hugging Face, we really need to think about, is it relevant to real world needs? What's the quality, what's the difficulty? Because, so we have models that say, okay, I'm better on this, but will it actually have an impact on early diagnosis? Will it actually give better treatment recommendations? And so I think there's still a lot to do on building these known pairs and these benchmarks. I think that these LLM parameters, there's so much, it's starting to become like a computer system. You can hardly find anyone who knows from top to bottom. In our lab, we have some deep learning experts that are used to play on learning rate, but the LLM experts, they just use always the same learning rate. So this is an example of parameter that some people vary, some people don't. And so there's a lot of different components, and the LLM experts are really doing text-based. And deep learning can be for images, for audio. So I think that as we move on, it will be harder to get a full grasp of what's going on. In Llama, from what I saw, I think there's maybe 5 parameters that influence reproducibility. I just tried one, temperature. But so for me, that's really a hard problem, other than using a loop to converge. I really don't see any way forward. And so if we think about FDA submission for drugs, where we really need high standard, rigorous, reproducible, I think we're still a long way to making these LLMs useful for these kind of applications. So you really need to think about which of your application can make use of it. Because a lot of questions will just give you hallucinations. If you ask ChatGPT about some very new thing, about something that didn't come up yet, it will tell you, yes, I know about it, here's all to know. One good example for me is when you ask to him about books. It can give you parts of the books that are really not there. And one of the new things I saw in ChatGPT is it's actually starting to include references. So I think that that's an important way forward. When it tells you that one drug is related to one disease, you can actually go back to the PubMed publication. So we need to constrain and control what it's doing. I see a lot of new hires that just copy-paste. For me, it's very different from copy-pasting from Stack Overflow. Maybe not so much, but I do think we need to think about it like Wikipedia, like we need the reference. And so of course you're not going to go back to it, but you need to know the rules to know when you can break the rules. Thank you all.
We'll open the floor to questions now.
ChatGPT is pretty good for convergent thinking. It has some difficulties on the outer edges when you get into divergent thinking. The large language models are trained on, the data sets that are out there, and it doesn't take into consideration it doesn't do a contrarian view. And I think that that's probably where we hold that niche to think, okay, so this is what we got. Are we missing some of the parameters? Can you speak to that?
Can you?
I'll use an illustration. Okay, I'm a divergent. And so let's say I'm in the open education field, and I say, okay, I ask ChatGPT, what are the ways that you can get your college degree? And it invariably never says the way that is currently available from edX and Coursera, which I had a hand in. It never enters that into the option. So what I mean to say is that anything that the models have been trained on, some of the research that's been done, Wikipedia, all these other types of things. Do you have a way to correct for the fatal flaw of AI in that particular area of, basically creative thinking outside the stupidity, outside the group, outside the box?
Yeah, so I think there's two parts. There's the part about the novelty and the part about the like more marginal. And so the novelty is kind of hard to fix because the model is trained at one moment. So you can do fine-tuning to keep it updated. The more marginal aspect is kind of what we're trying to do here, where because these, we can imagine that the general corpus on which it's trained, the relevant parts to biomedical labs are very small. And so I think that it will depend a bit on the models, and that's where we're going to need to do performance measurements and to find out which models just find the biggest groups and which models can find also the outlying groups. Yeah, so he's asking about like we're still talking about 1 million students. It's not really small groups, but when I say small groups, I'm meaning smaller than the other big group.
So you mentioned multiple models. Have you thought about trying some of the uncensored models that are out there to see if it gets around the safety issues? And beyond that, what sort of next steps would you want to go to with this research in the same domain or in different domains potentially?
Yeah, so the safety, I was a bit surprised. I thought that I would have less problems like this with local LLMs. I'm not so sure how to remove it. I heard about paper Bad Llama, for example, that was kind of saying that it was able to strip off the safety layer. So I think that's one of the way forward for that. The second question, where I'm going forward with this. So my big research project is suicide prevention. So this is what I'm currently focusing on. One of the, so this CUI dictionary is still kind of early stage, and I'm going to use it. And so I still have a bit of work to do on finalizing this use. This is the first time I'm using LLM to actually make the work. The BGE part was I've been using it for a few months. So one aspect we're investigating a bit is adverse effect predictions.
Hi, I had a question about the while loop that you put llama in. Was that inspiration from NVIDIA's technical report about putting DeepSeek in a closed loop verifier?
What was the first part?
How you put a llama in a while loop to get better results. Was that taken from NVIDIA's technical report on putting DeepSeek in a closed while loop as well?
No, it was just that I was noticing that it was giving me not always the same response. So what I do is that at each loop, I try to map it to my variable. If I can map it, then I take it out from the remaining ones. It's like every one that I can't map, I keep him into the loop until I find a mapped one.
So are you using like another model to verify that when it's sending its output? Are you verifying that with another model and then sending it back to the model to like reformat its response?
No, it's the same prompt, exact same prompt I re-send to Llama.
Okay, thank you.
Thank you, very impressive talk. I have a question at the end. You mentioned there's still a long way to go for biomedical LLM to be very useful in the industry. Do you have, in your opinion, I think you already demonstrated that the model is performing pretty well. In your opinion, like what is the biggest obstacle in the field? That is it like the data is limited or privacy issue or the regulation that still makes it a long way to go?
So the privacy issue is taken care of by the fact that it's a local LLM. I'm more concerned about the reproducibility. What I was saying was that maybe by doing these loops, by converging, maybe it takes care of this reproducibility. But like I had one example where I just couldn't map it. So if I was doing it like manually, so I still got my results, but maybe it wouldn't have converged. Basically, I would have still kept trying to map that variable. And so if you need to have human input that may be biased, if you, like FDA wants to be able to reproduce your analyses, so that's not something you can ask them. Like, oh, if it goes on 20 times, just remove that variable from your data set. That's really not the way you can do things.
That makes sense. Thank you so much.
We have time for a few more questions. Yeah, back there.
Thanks for the talk. My background's not in biomedical, so I'm interested when you're talking about the dictionary that defines the relationships and how it doesn't have that much coverage, or that's kind of like a challenge for you for semantic search, which makes a lot of sense to me. What do you think is being done or could be done to build something like that that can be used for the whole community? Or is there some focus on that, or is that just something right now that is a little bit insurmountable in terms of getting better data relationships defined?
So especially for the mental health, it's a bit complex to put in very neat boxes, and a lot of psychiatrists are talking about multidimensional, like gradient-based diagnosis, basically. Like you have autism spectrum disorder. It says spectrum because it's like not really a clear diagnosis. So I think that especially for mental health, it's we need to have more fine-grained. And so the second part you're saying about the relationships, I feel that these relationships are quite basic in most. Like if you say schizophrenia related to psychosis, it's very like low level. And when you start to say one medication is related to a diagnosis, you start getting a bit more complex. And I think that there's actually very little of these complex pairs. And so for me, that will be one very important way forward. So it takes a lot of time for the experts, for the clinicians to take time to do that. But I think it's really important.
Yeah, I work in defining data relationships. So I guess my question is really specifically like, is this something that people are working on? Like those subject matter experts, are they building that for the whole community? Like, is that kind of a project that's going on beyond maybe your particular project? Because it seems like, yeah, it's obviously applicable to your project and other projects as well.
Yeah, so UMLS is quite a huge project. There's a whole field of ontology learning. So it's basically the word is ontology, and you can find a lot of resources on that.
Yeah, I have 2 questions that are like, it's very possible you explained this and I missed it, so they might just be quick clarifications. But the first was about the reproducibility issues you had with Llama. I mean, I assume you were using like a larger Llama model, but I know for some of the smaller ones, like you can self-host those, and there are things like Llama CPP, right, where you presumably can see exactly how like, although, you know, I haven't actually bothered to like look at Llama CPP and see what's going on in there, but I assume it's possible to see like exactly how every single calculation is being done and what the parameters are. So I'm wondering like I guess I'm surprised that it wasn't possible to just get deterministic, like the same output. Like, could you speak a little more to like what the issue is with the reproducibility there and what would be needed to solve it?
Yeah, so a lot of people say that it's temperature, and what I saw was that it's actually not only temperature. And so I'm using 7 billion llama, which is kind of a small model.
Oh, yeah.
I'm using it local.
Okay.
So I could go into the source and figure out everything that's going on, but it would lose a bit the objective of winning time. So from my, like the latest things I've been looking at was, okay, what would be the other parameters that could influence this, that I could fix, and what I saw was that there's 5, at least. I mean, like from my understanding, maybe these 5 could, and so this will need further investigation.
And then my second question, which you I think might have answered, and I apologize if I'm just asking somebody else's question, was to do with embeddings, because my understanding is that there are like llama embeddings and like a lot of, like when models are openly released, like, you know, especially open models, like you usually can like get a vector model out of these like large language models. And so I'm wondering, if I understood correctly though, like when you used Llama here, you used it for its like generation, like to generate answers. I'm wondering like, is that a thing you're interested in doing, like using the embeddings for like a newer like large language model instead of the other models that you were using?
Yeah, so with the pipeline I talked about in the first part, it's a model we can easily plug into. So I've been focusing more on models that have been fine-tuned on biomedical data, and BGE in the literature was saying that it's quite good. So maybe rather comparing to commercial, and OpenAI has some good performance. So you need to take into account the cost of the tokenization, but maybe it can be worthwhile for your research. So it would rather be, I mean, we can try Llama. Let's see, but for me, in my guess, I think BGE is quite good. Maybe with Llama we would get a bit better, but probably not much. But however, with commercial embeddings, we could probably get a lot better. And after that, there's a question of fine-tuning, how you fine-tune. So I talked a bit about fine-tuning with suffixes. You can also do similar thing with the prefixes. And
Unfortunately, that is the time that we have for questions. Sorry about that.
we can talk later. I'm happy to answer.